Greetings, everyone. Here's the tutorial guide to the tutorial that we were supposed to have yesterday. So, we're supposed to do a problem 21.2, whereby you had to state whether the functions are concave or convex. So, in 21.2, these are the functions that you have to prove or show that they are concave or convex, whereby a is given by that function f of x equals to 3 exponent x plus 5x to the power 4 minus ln x. And then b, you can see that b is different from a. Your b is a multivariate function because it is explained more than by more than one explanatory variable there, of which is f of x and f of y, such that that fxy function is given by negative 3x squared plus 2y minus y squared plus 3x minus 4y plus 1. And then you have also c and d that are explained by three variables, which is x, y, and z, given by those functions right there. So now, for us to be in a position to state whether the function is convex or concave, we need to actually calculate the second partial differential function from the multivariate functions. And then from the univariate, just like a, you just have to get the second derivative of that function. And then if the second derivative is greater than 0, you conclude that the function is convex. And if the partial second derivative is not equals to 0 or is not less than 0, we conclude that the function is concave. So as you can see there under solutions, we have the first derivative for f of x, of which is the first term remains, because just 3 times e to the power of x. So the derivative of e to the x is just the same thing. So 3 there is just a constant, plus the derivative of 5x to the power of 4, that gives you 20x cubed minus 1 over x, since the derivative of ln x is just 1 over x. That's the first derivative. The second derivative is given by that guy, whereby this term remains the same. It remains constant. And then take the derivative of that term right there, this term right here, you get 60x squared minus. So for you to get the derivative of this guy, I used the quotient rule. And then that gives you the solution right here, 1 over x squared. So initially, the second derivative of ln x is just negative 1 over x squared. But because of this negative right there, so the negative and negative multiply tends to a positive there. So the overall function there, second derivative of f of x, is greater than 0. It's positive. So we conclude that the function is convex. The function is convex. Now let's move on to b, whereby in b we had that function. We had that function in b. So now we need to take all the partial derivatives with respect to our variables of interest. Sorry about that. So first of all, you need to get fx, partial f with respect to x. So that gives you a minus 6x plus 3. And then partial y with respect to f partial with respect to y is just 2 minus 2y plus 4. And then fxy is the same as yx, of which is that both equals to 0. And then the last two partial derivatives are going to be your second order, of which is going to be fxx, that is just minus 6. Then the last one is fyy, that is just minus 2, of which the second order partial derivatives are actually derived from your first partial derivatives, such that you form that second order metric. That matrix there is composed by your partial derivatives, your second order partial derivatives. So fxx, we said it's just that minus 6 right there, and then fyy is just minus 2 there, and then your cross partials, they're both zeros, as you can see there. And then from here, this metric helps us to calculate the second principal minor, whereby our leading principal minor here, h1, is just negative 6. It is always the second partial derivative of the first explanatory variable, of which in this case is x. So that's our what is called LPM, leading principal minor. So as you can see that negative 6 is less than 0, so we conclude that the function is definite. Conclude that the function is negative definite, and it is concave. It is concave. All right. So now moving on to C. Also in C, we have to get the first order conditions, of which are first partial derivative with respect to your variables of interest, whereby the first partial derivative of f with respect to x is that guy, 3 exponent x. Fz is just negative 1 over z, because we know that that function right there, ln z, the derivative of ln z is just negative 1 over ln over z. And then fy is just going to be 20 y cubed. The second order partial derivatives with respect to our variables of interest, of just x, y, and z. So it's just going to be that. They're listed down there. And then from there, you form a metric. From there, you form a metric of which your diagonal is just going to be the partial derivative, the second order partial derivatives of a variable of interest, as shown on that metric right there, whereby your leading principal minor gain is just that 3ex, 3 exponent x. So as you can see, that guy is positive. So it means this function is convex. The function of x, y, and z is convex. So now the last problem there, of which is D, it's a bit different from the problems that we have seen there. This is pure algebra, whereby you are just given only letters. How do you go ahead and actually comment on that kind of a function, whether it is convex or concave? Well, you simply apply your normal rules of solving a normal function. So here, you are also going to take the partial derivatives. So here, your variables of interest are still x, y, and z. All right, so that function is given by ax to the power of a, y to the power of b, z to the power of c. So the first partial derivative of f with respect to x, we are only going to partially differentiate the function of f with respect to x alone, and then the other terms just hold them constant, such that the power of x multiplies the whole expression, whereby you're just going to have a into everything, but now you less 1 from a, such that you have a times a to the power of x to the power of a minus 1 times the rest of the terms just the way they are. You just keep them constant. And then you do the same with y. You only take the effect of y exponent and then subtract 1 from that y exponent. And then the same applies to z. And then you go on ahead and get your second partial derivatives with respect to your variables of interest again. And then, so I think this is the most important part there, for you to be able to get your second order partial derivatives. And then from there, you form a metric again. You form a metric just like we did in C. And then you notice that fxx is your LPM, your leading principal minor. And from here, we can see that it is greater than 0. So this is the most important thing that you need to state there. To say that if A is between 0 and 1, A must be greater than 0 but less than 1. Also B and C, they must be both less than 1 but greater than 0. And then we'll conclude that F is concave. So yeah, that was all about yesterday's tutorial. If you guys have any questions, just DM me, and then I will explain all the parts that you guys would like me to explain. All right, there you have it. Cheers.